The average was a 101. Okay, just for sort of to see where things sit. Now, what does that mean? Again, after we set the grading scale, I heard a lot of kvetching and whatnot on during the exam. So we set the scale designed to give be reasonably good about partial credit and things like that. And anyway, the bottom line was that the scores were quite high, which is good. There were 17 120s, 17 115s, and then the counts dropped off. Is there a significant difference between this and that? The answer is obviously not. Okay, and so there will be a curve and stuff like that. The people I'm most afraid of, concerned about, were the people who were below 80. There were 8 people below 80. Okay, and these are the people who I'm most concerned with. Okay, so if you're below that, we have to sit down and talk, and have to figure out why that happened and what we can do about that. Again, I don't want to. The exam is only 20% of the grade, so there's plenty of room for other things to happen. But basically, if you're up here, that's fine. Okay, I mean that's clearly very good. Okay, I couldn't expect you to be higher. There's not obviously a lot of discrimination at the top of the range. So we'll see what happens when we have another exam and the final and the project and things like that. Here up to here is where I'm not concerned about really what's happening up here. Below here, that gets the scores start to thin out, and here I'd like to see some improvement. Here we've got some more serious problems. But up here, the test did not show anything that can be that concerned with. Okay. Any questions about what it means or what it doesn't mean? Okay. Again, there's going to be another. So the bottom line is you should be depressed if you got a 115. Okay. You shouldn't be unbelievably ecstatic if you've got a 120, because obviously there's a lot of action up there. But on the other hand, these are clearly the good and right grades to have if you've got them. Any questions? Don't know if that says anything. Okay. I don't really want to go over the test. Are there any quick questions about the exam that we would like to? I don't think I want to go through all of them because, in general, the scores were high. I don't want to go through all the problems. But are there any questions in particular? Okay. So if you're concerned about your grade, come back to talk to me. Come back to talk to the TA. Okay. If you think your paper was misgraded, the way I like to handle it, I like to have you write a note on the paper explaining why your test was misgraded. Okay. And then from the test from the note, we can try to figure that out. Okay. Hopefully that's not the case. Any questions? Okay. Very good. Okay. What I'd like to talk about more, okay, just as far as other bureaucratic stuff. The third homework is due on Thursday. Okay, so that actually, it's time to start looking at that one. Where the project proposals, I've been speaking to a bunch of students about their project proposals. And I think that's very good. So I encourage you, if you haven't yet come to see me, to start talking about your project. Some people are have ideas for projects on their own. They were interested in some aspect of discrete mathematics that has nothing to do with what we're, and it doesn't have to do with any of the projects I mentioned. Okay, that's perfectly fine if you find your own project. If not, come by and I can help explain, the projects we have to you. Okay, any questions? Okay, good. Okay. What I'd like to talk about today, last class at the end, towards the last class we started talking about Fibonacci numbers, and more than that, we used the generating functions to sort of solve the recurrence relation associated with the Fibonacci numbers. Okay, and so I showed you an example last class of how you can use generating functions to solve recurrences. And we're going to look at that a little bit more later on. Okay, in the next couple of classes, we'll get back to solving recurrence relations. Generally using them for solving recurrence relations. What I'd like to look at more is some examples, again, of how you use generating functions in terms of combinatorial interpretations of things, okay? That the idea of using generating functions, I mean, generating functions are kind of interesting things because they're really a symbolic way of manipulating, okay, sort of combinatorial objects. We saw back a few classes ago how multiplying two generating functions, properly interpreted, computed the distances between all pairs of points. That was a combinatorial thing being done by generating functions. Okay? What I'd like to show you now are some kind of clever ways of using generating functions to solve counting problems, okay, which are not going to reduce to sort of form a recurrence relation and solve them. We're going to actually form recurrences using generating functions. And so it's kind of a clever thing to watch. It'll look mysterious. Don't be afraid to ask questions if you have any. Okay? Any questions? So what we're going to look at now are some counting problems related to tiling a region, okay, by dominoes. Okay? So what is a domino? Everybody, I don't know if everybody has seen a domino. The way I'm used to thinking of a domino is it's something that looks like this. It's sort of a tile, a 2-by-1 tile that in the versions that of the game that I'm familiar with, they have numbers on them. That's completely irrelevant to what we're doing now. There's two things you deal with. Normally, there's two things you use dominoes for. One is playing games where the numbers matter. What's the other thing you do with dominoes? You arrange them in piles. You can knock them over. The numbers then are irrelevant. What is important then is that they are 2-by-1. They're all the same size, and they're sort of a unit squares stuck next to each other. So when we talk about dominoes, what we really mean is a tile simply that's 2-by-1. Okay? Any questions? And what we're interested in here is counting. How many ways are there to tile, okay, a k by n region with dominoes? Okay? I think first of all, suppose let's say we consider a 2-by-1 region, a 2-by-n region. How many ways are there to cover a 2-by-1 region, okay, with a 2-by-n region with dominoes? Okay, let's look at the special cases. A 2-by-0 region, okay, has no space in it, so you can cover them with no dominoes. There's only one way to cover them, which is basically the empty domino tiling. Does everybody agree with that? Okay, question?
What do you mean by region?
Okay, so what we're going to want to do now is the following. I give you a space that is a strip that is 2 by n. Okay, and I want you to cover it, to wallpaper this thing with dominoes. Okay, so let's say we have a special case of, let's say, a region that's 2-by-3. How many ways could we cover this? This is 2 by, actually, let's make it a little more obvious what it is. Actually, maybe we'll go to a completely different space on the paper. A 2-by-3 region. How many distinct ways are there to cover a 2-by-3 region by dominoes? Okay, by 2-by-1 dominoes. One way, I claim, would be to do like this, right? We could do that. Are there any other ways to tile this 2-by-3 region with dominoes? What other way? One way might be you could do it like this. You could leave this domino, the vertical there, and have it be 2 horizontal dominoes, right? Are there any other ways to do it? Okay, have the 2 horizontal ones come first, and then the other one, right? So this is another way. We're going to say this is different than that. So it's about ordered domino tilings here. Okay, you have the left-hand side of the wall, the right-hand side of the wall. You want to wallpaper the wall with dominoes. Okay, how many different ways are there to do it? Okay, any questions about what the problem grossly is? Okay, so what is it that I claim? I claim that if you have a 2-by-1 region, there is only one way to cover it by dominoes, right? Maybe should I zoom this up a little bit? Is this focused or not? Yeah, it looks focused over there. A 2-by-1 region, you can cover only one way by dominoes, right? That should be clear. 2 by 2 region, you can cover 2 distinct ways with dominoes. Okay? 2 by 3 region, we agree that there's 3 different ways to color them by dominoes. Okay? What we're interested now in is looking at combinatoric counting problems of how many ways can you cover a 2 by n strip with dominoes. Okay? Any questions about that? Okay? There are a couple different ways you can look at this problem. Okay? But let's look at it through generating functions. Okay? Just because it's sort of this is going to be the way that you would never think of looking at it. Okay? But you'll see some kind of interesting results by manipulating them in terms of generating functions. Suppose we let t be a generating function, okay, of all domino, let t be the set of all domino tilings. Okay? We could represent that by a list of all the domino tilings, right? There's the empty tiling, there's this, there's this, there's this. If you have a complete set of things, representing them by a generating function is just a different notation, correct? So there's no reason why you couldn't represent something that was a set of objects by representing them as the sum of objects, right? Okay, what it means to add this to that isn't clear, but for now, let's say it doesn't necessarily mean anything, okay? Until we actually get to the point where we're adding 2 things together and getting a sum, then we have to have an answer for it. But right now, it's just a notation. T is going to be the set of all domino tilings, okay? Any questions? It's sort of a polynomial. Now, if we want to think of all domino tilings that are 2 by n, what do we know about, okay? Let's say we want to think of all the domino tilings. I claim we can partition them into 3 sets of tilings. They're the tilings that have nothing in them, okay, of which there's only 1. They're the tilings that start with a vertical domino, and there's tilings that start with 2 horizontal dominoes. If we have a strip of 2 by n, is there any other possible way you can start the domino tiling? I mean, if you could take a domino and break it in half, yeah, you could have something like this. Okay, I mean, if you had a start of the thing, you broke your domino in half, you could put half the domino there, and then go from there, but that's illegal. We're not letting ourselves do that. So if you're going to completely tile the strip, it's got to start out with either a horizontal or 2 vertical, correct? What if we factor the list of all domino tilings as follows, okay? We can now collect all the domino tilings that begin with the 1 horizontal domino, and then put everything else in parentheses and have multiplication correspond to concatenation. This first, then this. Okay? Here we have the 2 vertical dominoes. Okay? 2 horizontal dominoes. And then factor out, collect all the ones that start with that. We can factor out this prefix. And what's interesting here is, if T is the set of all dominoes, okay, I claim, of all domino tilings that are 2 by whatever, I claim we get a recurrence relation for all the domino tilings. The set of all domino tilings, the infinite set of all 2 by whatever domino tilings, is equal to the empty tiling plus the set of all tilings formed by starting with this, followed any legal 2 by something tiling, plus the set of things started with the 2 horizontal dominoes, followed by any possible tiling. Okay? Looking at this, I think that we have a recurrence relation now that describes the set of all possible tilings in terms of itself. Okay? How many people sort of see what this recurrence relation means? It still looks like a mystical thing. Okay? But it should be reasonable to see that that's what we have. We have a recurrence relation that describes all possible tilings. It says any tiling is either empty, begins with 1 of these, or it begins with 2 of those. Any questions? Okay? Well, what else does that mean? I claim that by rearranging the terms of this function, I claim we can come up with a generating function by factoring out the t's. Using generating function notation, we can write that t is going to be equal to the blank. This is going to be t minus square t minus double square, sort of this thing, t. We factor that out, okay? That's going to be t times this t minus that t. I claim that solving for t, we can get an expression that looks like this, okay? How many people see where this generating function comes from, this closed form comes from? How many people find this, don't see it? I want to know where this comes from, okay? Some people don't see it. Well, this is simple algebra, okay? We're now doing algebra. Do you believe this recurrence relation? Okay? How many people here do not believe this recurrence relation? Okay? You got a question? Is that a question?
I have a question.
Sure.
Normally we consider the blank or something to be the equivalent of 0. And we kind of leave that alone on the expression for t on the top of the next slide.
Right?
We kind of leave that alone by itself. Doesn't that?
Well, it's not clear that is that a 0 or a 1 or something like that. Okay? This is a blank tiling. Okay? It's not a number. It's a blank. It's any more than is this a number? We haven't yet changed it as a number. If t is the set of all tilings, then I claim, which is what this is t is this polynomial, this function built of all tilings, then I claim that t has to be equal to this. That's all that I'm saying. Okay? Do you believe that? Okay? If you believe this, then I claim we can now just rearrange our algebra. What do we now know? This is saying that t equals blank plus delta t plus this t. If I rearrange those terms, that's t minus this t minus this equals blank, right? We can now factor out the t times 1 minus that minus this equals blank, correct? And if that's true, then t has to be equal to blank over 1 minus tile minus double tile. Okay? That's where this comes from. If you believe the recurrence, this is simple algebra. Okay? Any questions? Okay? Well, what does this mean? Okay? That seems kind of a weird thing. But what does this mean? Well, if you know what this generating function means, what does that generating function mean? What is a generating function of the form something over 1 minus something? Okay? What does that generating function mean? Okay? If this was a, some constant a over 1 minus z, you knew what that meant, right? That meant if you had something that was 1 over 1 minus z, that we had convinced ourselves last time was z to the 0 plus z to the 1 plus z to the 2 dot dot dot, right? So it still is, okay? Except z is going to be equal to vertical tile plus 2 horizontal tile, right? And if we had a constant here, that was simply going to be a constant multiplied out there, right? So I claim that we can interpret this expression, given that this is a generating function, this thing can be interpreted as this to the 0, which is going to be 1, right? Plus this to the 1, plus this to the 2, okay, dot, 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 with each term multiplied by a blank. That's exactly what this thing does. Okay? And so I claim that if we interpret this as a generating function, this is what we actually get. Okay? Any questions? Well, what does that silly thing mean? Well, we said that multiplication in this module is interpreted as being concatenation, right? So what is blank times this plus this? Okay? That is simply this plus this, right? What is this tiling plus this tiling times itself? Let's just take a look at that. If we're defining it as concatenation, the plus sign is basically being comma, okay, and this thing is being concatenation. What is this plus this times this plus this? Well, you know how to multiply polynomials. That is this plus this plus, what else did I want to, okay, I'm not going to get myself confused. This, I've taken both times that. I'm now going to take this plus, isn't that what it is? Okay, the result of multiplying those two? Any questions? What's interesting about this, if you take a look at this thing, I claim this expanded. T was originally the set of all tilings, right? After we've done operations, if we expand it, okay, it should still be the set of all tilings, right? The set of all polynomial corresponding to all tilings was T. I now have multiplied it out. This should still be the set of all tilings. Is this in fact the set of all tilings? I claim it is. Okay, only in a somewhat different order than it might have been. What does the first term correspond to? All tilings made up of 0 blocks of things, right? Where we define a block as being either this or this. What are the terms collected in the first thing? All tilings made up of 1 block. Here we have all tilings made up of 2 blocks. My claim is any 2 by whatever tiling can be broken into a certain number of blocks. Okay, is what I mean by block clear? Okay, meaning that it's something that you sort of bisect it and it leaves a legal separating tiling. It leaves a legal, sort of, you cut it and it's legal domino tiling. There's no domino gets cut in half. Okay? So what's kind of interesting here is, if you look at what I've done, this polynomial operation has basically grouped the dominoes, all domino tilings, according to the basic number of blocks. Okay? Any questions about this? Okay? If this seems ridiculously mysterious, let me know. Okay? Or if there's any questions about it. Right? Because again, there's nothing that we did that was violently unreasonable. And as you can see, by when we expand it, the interpretation is exactly as it should be. Okay? Any questions? Well, let's continue on to this thing. Okay? T is now a generating function that enumerates all tilings. Okay? If we want to actually count tilings, what I claim we can do is sort of relax what these, somehow if you want to count tilings, you want to find a way to sort of modify this generating function to relax it so that things that you want to be together get grouped together. Okay? That's really what you want to do in order to count it. Okay? So what we're going to do now is sort of relax this generating function to enable us to count with it. Okay? Let's say we want to count the distinct tilings that we can form from K horizontal tiles and L vertical tiles. Okay? What could we do? Well, we have up here a generating function for all tilings. Okay? What if I define a new generating function, okay, that is going to be equal to all tilings I can form, okay, from all sort of where each thing in term in the polynomial is going to be a combination of a number of vertical and horizontal tiles, okay, and the coefficient of it is going to be the number of tilings that can be realized that way. If I want to count how many ways there are to tile things such that I use J vertical tiles and K horizontal tiles, what can I do? Okay, I can go and I can take a look and just simply pull out the right term of this expression and look at its coefficient. Its coefficient will be to count what that actually is. Okay? Any questions or conceits? Okay? Question?
Whatever tilings that you have will be the coefficient?
Right. T prime is going to now be a new generating function that is going to count for any combination of horizontal and vertical tilings, how many tilings there are of a 2 by something strip using exactly that many tiles. How many tilings are there using 1 vertical domino and 2 horizontal dominoes? Okay, how many of them are there? Okay, how many? 2. What are they? Okay, they're this thing first. I mean, the two choices are the sort of tall domino followed by the 2 horizontal dominoes, or the 2 horizontal dominoes followed by the tall domino thing, right? So if I could get a polynomial like this, then I claim, if you want, how many ways are there to count, to tile the things with a certain number of horizontal and vertical dominoes. I simply have to find the right term, okay, and read off the coefficient. Correct? Well, how can I get this kind of a thing? My claim is, over here, I have a polynomial that is counting all possible tilings. Correct? This plus this plus this. This counts all possible tilings. Suppose I want to group the terms so that I collect all things with the same number of horizontal and vertical tiles. My claim is I can take this thing and say that this, if I want this tiling, let's say this tiling to be the same as this, I can replace it by every time that I can instead interpret my function here as being this is a vertical tiling. What I claim is this, okay, is the generating function, that by taking the, actually I think I've got too many things on the board. This, we agree, is a generating function of all tilings, right? Suppose I define the following generating function, T prime, where instead of having the positions of the tilings specified, I say that this chunk has 2 horizontal dominoes. Let's just call that 2 horizontal dominoes, horizontal squared. Here I have one that is going to be 1 vertical plus 2 horizontal, and I'm squaring that. What happens when I square this term? Okay, what is this plus this squared? That's going to be this plus this plus it's this plus this plus tall 1 squared plus this times that. That's going to be another instance of that, plus this times this. Okay? Sorry, I can't see it. That's a good one. What happens when you square this thing? I claim that you can now get a function. Okay, if you look at it this way, what you're now getting is there are 4 terms, but 2 of them are now identical. Okay, and the ones that are identical are going to be the ones with the same number of horizontal and vertical tilings. Okay? If you think about it, if the original function, okay, did indeed enumerate every single domino tiling, this function is also going to enumerate every single domino tiling. Okay? The difference is that it's going to allow us, if we group similar terms, the terms that will get grouped similarly are going to be those with the same number of horizontal and vertical dominoes. Okay? Any questions here? Okay? How many people are thoroughly confused? How many people are not confused? Okay? More people admit to not being confused. Well, what does that mean? Relaxing that generating function, I now have this new generating function, which I claim is going to enumerate every single domino tiling, but group terms together if they have the same distribution of dominoes. Okay. What is this series going to look like? Well, it's the empty one, plus this thing squared, plus this thing cubed. This is a geometric series, okay? Therefore, the closed form of this generating function, I claim is 1, or blank actually to be precise, blank, since we factored out the blank, over 1 minus z. This is the generating function for z squared if this plus this squared is set to be z, right? So now we have this as a closed form for this generating function. Any questions? Okay. What does that mean? Well, let's look at this thing. This thing, the generating function for this, okay, I claim by expanding it is the power series, okay. This thing expanded, we agree, is the power series vertical plus horizontal squared to the k. The sum as k goes to that. Okay, correct? This is exactly what this is. We could have actually read this off directly from that without going to the closed form. What is vertical plus horizontal squared to the k, summing that up? Well, my claim is this plus this raised to the k, we can apply the binomial theorem to. Why? If you have x plus y, just write that down. If you have x plus y to the k, what does the binomial theorem say that's equal to? Okay. The sum, yes? Oh, sorry, okay, sorry. Okay. Sum is, I goes from 0 to k of what? Okay. K choose I times x to the I times y to the k minus I. Correct? This is true, okay, because the binomial theorem is true. Therefore, I claim, what is horizontal plus vertical plus horizontal squared to the k? I claim that is the sum over all k of k choose j horizontal to the j times this thing to the k minus j. Okay, correct? Just by the binomial theorem. Where does this 2 come? Well, this thing is really, y is really this squared. So if that's true, this is going to be this squared to the k minus I, or you multiply the exponents. That's where the 2 comes from. Okay? Any questions about how we got to here? Or would someone like me to repeat that? Okay? I realize I'm going through this a little bit slowly. Okay? Because it's kind of a mysterious thing. But what do we now know? Well, this is actually kind of amazing. Now we can, if we did a little variable substitution just to clean things up, suppose we say that m equals k minus j. This would be 2 times m. If m equals k minus j, then I claim that k equals j plus m, right? So without loss of anything, we can write it as this. Okay? What does this mean? This tells me that the coefficient of the the term that has j vertical dominoes and 2m horizontal dominoes is j plus m choose j. Correct? How do we interpret this? This says that there are, okay, if we sum this thing up, j plus m choose j tilings which contain exactly j vertical and 2m horizontal. Right? Why is that? Because this is the generating function of all domino tilings collapsed by by their distribution of dominoes. We are now writing this thing out. This thing has now just been expanded. So it lists all the domino tilings, all possibilities of j and m that add up to legal domino tilings, and it lists the coefficient of that. My claim is it's just reading off the coefficient counts the number of such tilings. Okay? And so what this really says is that there are j plus m choose j domino tilings with j horizontal and 2m vertical. Any questions about that? Okay. Now this is now a simple enough thing. We may want to ask ourselves, is there a more direct proof of it? Okay. Can we come up with a nice combinatorial proof that in fact that there are j plus m choose j tilings with this thing? Is there a more direct proof? Well, a way to think about it is as follows. If I'm going to use my j tilings, okay, what is actually, now let's think about it. Does this make any sense? We know that in any such tiling that's 2 by something, okay, if it has a vertical domino, what role does that vertical domino do? It has to cut across the whole width of the strip, right? What do we know is going to have to happen with the pairs of, with the vertical dominoes, or the horizontal dominoes? Okay? If they're going to be it's going to be a legal 2 by something tiling, they're going to have to exist in pairs, right? There's no way that they can be staggered. So what I claim actually is, you can think of any domino tiling of 2 by something as consisting of j vertical strips and m 2 strips, right? So what does that mean? The number of distinct tilings can be as the number of places to choose where to put the vertical strips, right? You've got j plus m modules that you're building the thing out of, okay? And the number of distinct tilings are the number of distinct places to put the vertical separators, of which there are j plus m choose j. Any questions about that? Okay? The combinatorial argument should make sense. So once you see this is the answer, you certainly should be able to go back and understand, yeah, this I understand. This looks amazing, but in fact it's just a straightforward application of the algebraic tools we've used, okay, on an object that counts everything. Okay? Any questions? Okay? We're using the fact that multiplication can serve as the form to model concatenation. Just like when I was talking about the distance generating functions, multiplication can be used to model the subtraction of distances, okay, on the line. Any questions? Okay? Any questions about 2 by n domino tilings? Okay? Good. Now, suppose we want to count how many total number of tilings there are. Okay? Here we have a generating function that counts how many tilings there are, partitioned according to, the number of types of each domino. Suppose I want to now come up with a way to count how many dominoes are there, tilings are there, of length n. Okay? How many ways can we do that? Well, one way to look at it is as follows. Let's now relax this generating function even further, where all we want to do is to count. We want to somehow collect all tilings together which have the same length. Okay? So which domino tilings would we want to collect together now? This has length 2. This has length 2. Correct? If we want to collect the dominoes based on length, we want to now change our variables so that when we combine terms, this is equal to that, or this has the same, these things have the same exponent. So the terms get collected and they get added up to the coefficient. So what could we do? I claim if I take that underlying generating function, okay, and now expand it as follows. Suppose we consider the generating function. Here we have, suppose we interpret the generating function like this. What does this mean? This is basically the infinite sequence of tilings. This is a tile of length 1. This is a tile of length, a module of length 2. I claim that if we replace this by z, because this is z, if we want, let's say, have a variable z denote the length of the tiling. This is a tile of length 1. This is a tiling of length 2. If we expand this and multiply it out, what I claim is all tilings of equal size will collapse onto each other. Okay? Do people want to see an example of that, or do people sort of see what's going on? Who wants an example? Some people want an example. Fine. What happens if I now take my underlying domino tiling, that was this thing here, okay, and instead expand this thing, where I think of this as being, this is a domino tiling of length 0, right? That's the domino tiling of length 0. This is a domino tiling of length 1. This is a domino tiling of length 2, correct? So far, how many tilings of length 2 are there that we've seen? Only one of them, right? What about this? This is a domino tiling of length 1, and the choice of either a domino tiling of length 1 or length 2 concatenated with one of length 1 or 2, correct? How many domino tilings do we get by concatenating one of these with one of those? We get 4 of them. What are the lengths that we would get by concatenating one of these modules with another one of these modules? What's the shortest one? It'll be length 2, right? And that's for concatenating this with this. Or equivalently multiplying z1 plus z2 squared times z1 plus z squared. This is z squared plus 2z cubed plus 1z to the 4th. Right? And what does that mean? That means that when you multiply these tilings, we've collected it so that you've got the one tiling of length 2 of n equals 2, the one tiling of n equals 4, and the two tilings of n equals 3. Okay? Any questions about this? Okay, or any, comments right now? What I claim is if I go through and do this for all the tilings, and I collect together all the terms that are, that are equal to this, Okay? My claim is that what I'm going to be getting is exactly a count of how many tilings there are of length n. That should be clear now. And if not, let me know. This generated all tilings. This, by relaxing the variables, made it so that things that got collected would get collected according to their size. Okay? And therefore, the coefficient of the z to the n term is exactly how many tilings there are of that. Okay? Any questions? Okay? Don't be afraid to ask, because things may get even murkier a little later. Okay? That's why now might be a good question time. Any questions? Okay? Well, what does that mean? Let's stop and think about it. That tells me that we can interpret the set of all tilings. If we want to do it by length, we get a generating function like this, because that's now z1 plus z squared. If we expand this and count the number of things, that I claim would be the coefficient of the z to the n term. That will tell me how many tilings there are of length n. Okay? Any questions? Does anybody have any idea what this expands to? Let's look at this. Have you seen this generating function before? Okay. The Fibonacci numbers. This generating function came up in the solution of the Fibonacci numbers. Okay. Why does that mean? Well, if you go back, turn a couple pages, you can verify that's true. If, in fact, this is the generating function for the Fibonacci numbers, what does that mean about the number of tilings of length n? Okay? What does that mean? It's given by the Fibonacci numbers, right? If this was the generating function for the Fibonacci numbers, and this was a generating function for us, I claim that this has to count the number of Fibonacci numbers. Okay? Any questions? Can anybody give me a more direct proof that the number of tilings of length n is given by the Fibonacci number? Okay? Any ideas how you would prove that? Okay. Question? Or any ideas? So I think what the idea is, okay, which is right, okay, what I think it is, okay, and I think it is that if you took a look at it, when I factored things out, there was a recurrence relation that said that all tilings either started with this thing, okay, unless they were the uninteresting tiling of length 0. Any tiling either started with a flat tile or it started with a pair of tiles, right? So what is the argument? If t is the number of tilings of length n, my claim is that any tiling either starts with a 1 horizontal tile, which meant it can be followed by any tiling of length n minus 1, right? Or it starts with 2 of these guys, right? In which case it can be followed by any tiling of length n minus 2. Okay? And so the number of tilings of length n is equal to t of n minus 1 plus t of n minus 2. This is the Fibonacci recurrence relation. Okay? And so presumably this evaluates out to be the Fibonacci numbers. Okay? Any questions? Okay? Question?
Can you use induction to prove that T of n is equal to the generating function?
The question is, do we prove that it's equal to the generating function? The way that we're going to prove these things is sort of by analogy. It's sort of a combinatorial argument. Okay? I have proven to you before that this generating function is the generating function for the Fibonacci recurrence. If that's true, you should be able to solve the recurrence the way we did last time. Okay? So if you believe that this is the generating function for it, you just have to go from there to solve it. Okay? Once we saw the answer, then in fact we could come back with a combinatorial argument that in fact the number of tilings were counted by the Fibonacci recurrence. Okay? And we could work from it that way. So what's interesting is we're seeing a couple different ways to look at it. There was the very clever approach, which I'll call here the combinatorial argument, of looking at it and generating a recurrence to count directly. The other approach was to simply manipulate them all as a generating function, and then see what logically falls out of that. Okay? Any questions? They require different kinds of insight. This, I claim, is pure algebra. Okay? And no more or less interesting than pure algebra. Okay? This required sort of just seeing it. Okay? And you have to later show that they're the same things. Any questions? Okay? One minor point, again, it should be clear that by now that the Fibonacci recurrence is lurking in the number of tilings there. Just because the Fibonacci recurrence is lurking, does that necessarily mean that there's one tiling, one tiling of length 1, if we have n here, that the number of tilings? Is there one tiling of length 1? How many tilings of length 2 should there be? 1. Tilings of length 3, 2. Tilings of length 4, there should be 3, and so on. It may or may not be the case that these numbers work out exactly. It may be shifted in this case, okay? Or it may be that we're starting from different assumptions. Let's say I went to the store and bought you, let's say that there may have been a different number of tilings of length 1. The basis cases might be different. So there are other sequences of numbers, other than the pure Fibonacci numbers, that will obey this recurrence. Correct? Because the sequence is parameterized by the recurrence and also the basis case. Correct? The basis case for Fibonacci was that for 0, that f of 0 was 0 and f of 1 is 1. Okay? There's another case of that I think where there's other instances of this recurrence that come up a lot. There's something called the Lucas numbers, which are nothing more than these things I think started with the term 0 and 2. Okay? And these sometimes come up. But basically, once you have the recurrence, you can solve it and then work backwards to get the basis condition, to see how the answer changes for the basis conditions. The insight is that the recurrence applies. Any questions? One way or another. Okay? We can do similar things. Okay, let's just take a look at this thing. To look at 3 by n tilings. Let's just try this very quickly, just to sort of show you a little bit about what can be done. We can do similar ideas to count how many tilings there are that are 3 by n. What does that mean? Well, now it's going to be a little bit more complicated, because in general, if you have a 3 by n tiling, domino pieces are only 2 by 1. You're going to no longer have clean divisions, okay, as often. You might not have all clean divisions of modules. Modules are now going to be broken tilings as well. Okay? Is that sort of seen that the number of tilings of 0 is 0? The number of tilings of a 3 by n tiling, where n is odd, I claim there are no such tilings. Why? Because if we have a 3 by odd number tiling, what happens when you multiply an odd number by an odd number? An odd number, right? How can you make an odd number out of an even number of cells, since each cell contains 2 dominoes, right? So you should be convinced that there's no way to do this for odd numbers of n. Okay? Now, for even numbers of n, it gets more complicated. For 3, I claim there's 3 by 2. There's 3 tilings, 3 by 2. We could either have the 3 horizontal dominoes, the vertical domino on top resting on 2 dominoes, sort of pi, and the upside down pi, if you want to think of it that way. Okay? Any questions? The interesting thing is we can define a generating function on all domino tilings of 3 by n in a similar fashion, even though there are these broken domino tilings. How do we do it? We can observe that any tiling that is 3 by n starts with either a module of 3 horizontal dominoes, puts a horizontal one on a vertical one, or a vertical one on a horizontal one, right? And we've got a broken tiling afterwards. My claim is that you can define a similar recurrence relation, okay, for 3 by n tilings. Let U be the set of all 3 by n tilings. We could factor all 3 by n tilings to either being the empty tiling, all tilings that start with that, all tilings that start with that, and all tilings that start with that. All tilings that start with 3 horizontal ones are the 3 horizontal ones followed by any legal 3 by n tiling, right? So this is going to be the same variable. If we start our tiling with this, what we now want to count are, it has to be followed by a tiling where we've got 2 at the bottom and then even leaf put, right? The tilings that follow this are different than the tilings that follow that. So we're now going to define 2 other symbols, V and upside down V, for the generating functions of the tilings that match with each of those. Okay? Any questions? Okay? That said, the interesting thing is we can define each one of these guys, the generating functions for these fractional tilings, in terms of the full tilings. Because if we have a tiling that looks like this, then we know that it either starts out with that or it starts out with that. If it starts out like this, we've got a legal tiling after it. If it starts out like this, then we've got the other kind of fractional tiling after it, right? If you look at the notes, okay, I claim we can define a even more complicated generating function solely in terms of itself that describes all 3 by whatever domino tilings. And then going through and doing the algebra on that, we can now collect for U, solve for U. We get an uglier looking generating function. But again, this can be expanded to count how many tilings there are. Any questions? Okay, I don't want to go through the algebra here. What I urge you to do is to go through this and verify for yourself that the number of see where these functions come from. See how these things define the recurrence relations. Okay? And that somehow it gives us a way to manipulate all the combinatorial objects. So you should get as far as defining the recurrence relations. You don't know how to expand them. Okay? But take a look at it. I urge you to go through them just to get a handle of that. Any questions? So this is interesting because it gives you a different way to think about recurrence relations. Okay? And combinatorially thinking about these things and manipulating them algebraically can be a useful thing. Any questions? Okay, good. One other little domino problem, which I'll just sort of take a look at, which is sort of a famous Domino's problem. Okay, it's sort of historically the question that gets asked most on PhD qualifying exams, although not here. Okay, for those of you who are PhD students. Suppose I give you an n by n domino, an n by n checkerboard. Okay, here we have an 8 by 8 checkerboard. How many ways are there to cover a checkerboard, okay, without, an n by n checkerboard for a given value of n? You'd like to cover it so that it's without corners. Okay, so you want to cover the dominant. You're saying that you're willing to leave these two pieces blank. How many ways are there to cover an n by n fractional checkerboard by Domino's? Okay, can anyone look at that and tell me how many there are? Let's try for n equals 1, for n equals 2. How many ways are there to cover the dark spot by Domino's? Okay, how many? 0. What about n equals 3? Now we've got this thing here. So right now this is the dark spot, right? How many ways are there to cover that with Domino's? Okay. How many people have found one? How many people convince themselves that there's 0? Okay. In general, why are there 0 ways to cover any square, any checkerboard by with these dominoes with 0? You observe that if it was a checkerboard where you have it colored as a checkerboard is covered, every domino covers a a red square and a blue square, right? Suppose I have an n by n checkerboard. How many red squares and blue squares are there? Okay. Well, there's n squared, what do you call it? N squared squares, right? In a, if n is an even number, there's going to be half red and half blue squares, right? If the corners are always different, the same color, subtracting out the corners means that there's strictly less white squares than there are red squares. Okay, I know I'm changing colors on you a lot of times. But bottom line is there's fewer of these colors than those. Since every domino covers both, has to cover both colors, that's a quick argument that for any n, there is no way to do that. Any questions? Okay, that should sort of be believable. Okay, and it's a good example again how if you look at the problem combinatorially, sometimes you can do amazing things without calculation. Any questions? Okay, good. What I'd like to do now for the rest of the class is just review a little bit more about the interpretation of generating functions, okay, of certain rules on manipulating generating functions of algebraic terms, okay, so that we have this as sort of, there's certain elementary operations that shouldn't look so frightening because you understand them, okay. What happens if I'm given two closed forms of generating function, the closed forms of two generating functions, f of z and g of z? These are two generating functions. I give you the sum of alpha times this plus beta of that. What is the interpretation of that? Well, we interpret this as we expand this generating function, we get the sum of f sub n zn, correct? Over all values of n. We expand this thing, get the sum of gn times zn, okay, for all values of n. We multiply this by alpha. What does that do? It multiplies each term of that generating function by alpha, right? And this by beta. My claim is that an expression like this is written as the series, okay, over all n of alpha f of n plus beta f of n times z to the n. Okay? How many people believe this, see this, and understand this, feel it in their bones? How many people don't feel it in their bones? Raise your hands. Would like me to try to explain it again. Okay? Any questions? Okay? What does it mean when we take a generating function and multiply it? But by the definitions here, what I'm saying is we're sort of using the default definition, which I think it should be that when you have something that looks like f of z, that is the sum of little f of n, z to the n, over all n. Okay, that's what we mean by the big capital F of z is a closed form for the term f of n, z of n. Okay? What is, maybe I'll zoom this thing in a little bit. What is zm times g of z? Well, g of z is just a polynomial g of n times z of n. Multiplying it by zm means that what is the coefficient of the zn term going to be? It's what was the coefficient of the z to the n minus m term. Because multiplying it z to the m times the z to the n minus m term is going to give us z to the n, right? So I claim that when we multiply a closed form of a generating function by z to the m, what we're really doing is doing this, which is a right shift. How many people feel it in their bones? Okay? How many people do not feel that in their bones? Question.
Can you expand on it a little bit?
Can I expand on it? Okay, sure. Okay, what does this mean? Well, let's write it out. This is nothing more than saying this is z to the m times, what is g of z? g0 plus g1z plus g2 z squared dot dot dot, right? So what does this mean? This is g0 z to the m plus g1 z to the m plus 1 plus g2 z to the m plus 2 dot dot dot. This thing can be written as, I'm sorry, I guess you want it zoomed down, right? This thing is going to be equal to what? The sum over all m of gm, actually let's try this thing, gm, actually let's say all n, excuse me, of g z to the n plus m, correct? Let's take a look at that. You see how where the variable manipulation comes from? And this I claim by just doing a variable change. Suppose I want to write this thing as, what you call it, in another way. I could write this thing as, let's call this thing, suppose I say that n equals n plus m. I could rewrite this as this, g to the this minus that, okay, this minus that, which is m minus n. Take it. Okay, what did I claim this thing was here? If I interpret this as n, this is going to be m less than that. That's why you get g to the n minus m times zm. Okay? Any questions? Okay? It should be, it looks mysterious, okay, somewhat. But again, you have to get used to that by now. Okay, or soon. Any questions? Okay? What does it mean?
Is there a better notation to have it in that form than what you had?
Why is this? Okay, here you'll say the question is why did I change variables? And the reason is we're usually interested in what is the coefficient of the nth term. Okay, it's easier to think of it in terms of that. Okay, because remember we're going to use this to read off what is the value of a counting thing, right? So that's why it's probably better to keep it the exponent as n and to renumber things. For example, it would be easier if we knew that this was f of n minus 3. We'd say, well, the coefficient of the nth term is the Fibonacci number of n minus 3. Something like that. Okay? Any questions? What if we have, sort of look at something else, okay? This was corresponding to, okay, trouble. Okay, now we're in big trouble. All right. No. Okay. This is wrong. Sorry about that. Okay, sorry, I'm now in trouble here. Let's even carry on for the rest of the. Here we go. Good. Okay. Here we've got what was a right shift when we multiply it by it. What happens if we divide by it? Well, now the corresponding operation would be instead of moving the thing to the right by n terms, we move it to the left. We still have a z to the n term, but the coefficient is now bigger than it. If here, as is our convention, we now have the sum of all terms that are for n greater than 0, equal to 0, when we took g of z and divided it by z of m, somewhere we have to worry about the terms, okay? What was the coefficient of g0? Well, g of 0 divided by z of n, we would now have a negative exponent associated with it. And so notice here's what we got. Here we've got the terms with negative exponents. If we insist that here the sum be n be greater than 0, okay, that's why we have it on the other side. Okay, basically it says that if you're going to shift it over to the left enough places where you go beyond the initial point, you've got to carry on for those other terms. Okay? Any questions? I'm belaboring that point. Okay? What about this? What is g of z? G of cz? Well, we know that g of z we defined as g of n, z of n. Well, if we're replacing z of n by c times z, this is g of n times c z to the n, or c to the n, z to the n. Correct? So we have another constant in here. It simply gets written out as an exponential function. Correct? Any questions? That shouldn't be mysterious. If you did your algebra, if you did calculus, which I know all of you have taken, okay, what happens if you take the derivative of a generating function? This is sort of a strange operation, okay? What is the derivative of g of z? Well, if g of z is equal to g0 plus g1z plus g2z squared dot 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 gn z to the n, the derivative of it, the derivative of it is going to be, this is going to go away. This is going to be g1 plus 2gz g2z plus, in general, n gn z to the n minus 1. Correct? That's what happens when you take the derivative. So if you look at that, that's kind of an interesting thing. Again, normalizing the variables so that we get, sorry about this, so that we keep our exponent z to the n. What's interesting is that by taking the derivative of our basic generating function, we've created a generating function that counts the natural numbers. Okay? If you want, what is the sum of your fingers if you have n fingers? Okay, each finger counts for 1. This is a generating function for that. Okay? Any questions? It gives us a way to get a counting variable in there as a coefficient. Okay? And likewise, if we now take z times gz prime, that actually will raise the exponent here and make the nicer looking n times gn zn. Okay? Any questions? Likewise, if you take the integral of a generating function, it's no different than taking the integral of any other polynomial. Now, instead of multiplying by n, we're now dividing by n. Okay? And that should give you a way to realize that generating function. Any questions? We saw earlier on that if you multiply two polynomials, what you're really doing is convolving the terms, right? The coefficient of the z to the n term is going to be the z0 term in one plus the zn term in the other, times the z1 term in one, zn minus 1 term in the other, bop, 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 bop. Multiplying two generating functions gives you convolution. Okay? And that should be a perfectly believable thing. Any questions? Likewise, we talked about it before, the special case where one of these functions, the f sub n is always 1. 1 times anything is just going to be anything. If we multiply it by the generating function for all 1s, we get the special case of the generating function of all prefix sums. And that we looked at before and should be believable. Any questions? Okay, so think about it. Go through these things. These moves, the basic steps should be fairly believable now. Okay? we're going to use to build more complicated things. Any questions? Thanks for your attention. See you guys on Thursday.